In this video, we're going to explore a method for finding strongly connected components of a graph from Skiena's The Algorithm Design Manual. Strongly connected components are subsets of the vertices of a directed graph with the property that from any vertex in the subset you can get to any of the other vertices in the subset. There's a picture of a directed graph with its strongly connected components circled right here, taking for instance this circled strongly connected component in the upper left hand corner. Starting at vertex 1, it's possible to get to, say, vertex 4 by traversing the path from 1 to 2 and then 2 to 4. It's also possible to get from 4 to 3 by traversing the path from 4 to 1 to 2 to 3, etc. So it's possible to get everywhere around this strongly connected component within this graph. Okay, Skiena gives an algorithm for actually doing this, for finding these strongly connected components given the graph. We'll only mention the code now and then, and we'll talk about how the algorithm works kind of visually on quite a few examples. So we start with this very simple example, which is a graph consisting of two vertices and one edge connecting the two of them. This graph has two separate strongly connected components. Each of its vertices is its own strongly connected component. The reason for that, of course, is that it's not possible to get from 2 to any other vertex, so it has to be in its own strongly connected component. And although from 1 you can get to 2, you can't get from 2 back to 1, so 1 is also in its own strongly connected component. Now, we can confirm this visually, but let's talk about how the algorithm would work that we actually use in order to find this. So the first thing that we do is begin our depth first search, incrementing a time marker. And we'll start our depth first search at vertex 1 here. We set the entry time equal to our time marker as we first enter this vertex 1. And we set DISC, which stands for discovered, equal to true. So we have now discovered this vertex. And we push this vertex on what we call the active stack. The active stack is going to be a place where we keep vertices that have not yet been assigned to a strongly connected component of the graph, despite the fact that we have discovered these vertices. They just have not yet been assigned to a strongly connected component. So we push one onto the active stack, and then after we do that, for each vertex, we are going to explore the edges that come out of this particular vertex. So there's only one edge to explore here, the edge from 1 to 2. And we see that 2 has not been discovered. Discovered is false, which means we are going to discover vertex 2 and conduct a depth first search on it. So we discover vertex 2 at time 2. We mark discovered is equal to true, and we push vertex 2 onto the active stack. Now, following our general procedure, once we enter a vertex and discover it, our next step is to explore all of the edges out of that vertex, but there are no edges out of vertex 2. So we are done with vertex 2, or at least exploring all of its edges, and now we have to process it late, following this procedure given in Skiena. Here, process vertex late. Before we can leave the vertex and move back to the vertex we were processing before, its parent. So in order to process the vertex late, we first check to see whether low of the vertex is equal to the vertex number itself. Now the low of a vertex is the earliest vertex in the graph to which there is an edge from this current vertex. So the earliest vertex from vertex 2, there are no actually earlier vertices in the graph to which there is an edge from vertex 2, and so we say that the low of vertex 2 is actually just vertex 2 itself, even though there is no vertex, edge from vertex 2 to itself. In that case, where there are no edges to earlier vertices, we just assign the low to be the vertex itself. Okay, so if the low is the vertex itself, then we have discovered a strongly connected component. And it's clear to us, at least in this example, that 2 is its own strongly connected component because, well, it's not connected to anything else. You can't get anywhere else from vertex 2. And we will talk about in more detail with other examples why it works in other cases as well. But we found a strongly connected component. What we do is we pop 2 off the stack, and we assign SCC, strongly connected component of vertex 2, to be 1, which means that the number of the strongly connected component that 2 is a member of is 1. Now we have finished processing vertex 2 late, and we are going to leave vertex 2. On the way out, we mark vertex 2 as processed, that is PROC is processed and processed equals true, and we increment the time marker as we leave vertex 2. Okay, we return to vertex 1 where we were in the midst of processing all edges from vertex 1. Now there was only one edge from vertex 1, so we're done processing all edges from vertex 1, which means we now are going to process vertex 1 late. We first check to see whether low of vertex 1 is equal to itself, which it is, and in that case we are going to pop components, which means we increase the number of components found by 1. We pop vertex number 1 off the stack, and we assign low of vertex, we assign strongly connected component of vertex 1 to be the current number of components found, which is 2. So the first strongly connected component we found in this graph is vertex 2 all by itself, and the second strongly connected component we found in this graph is vertex 1 all by itself. Our algorithm now terminates. Okay, now of course this is a super trivial example. The next slight level up from here is a situation that's almost exactly like the one we just processed, except for that we have this back edge now. So we're going to run through the algorithm very quickly from the beginning to get up to the point of interest. So we increment the time marker by 1, and the entry time is increased by 1, and discovered is equal to true, and we push vertex number 1 onto the active stack, and then we begin exploring the edges, starting with this one. We discover vertex 2, increment the time marker by 1, entry time is 2, and discovered for vertex 2 equals true. And then we are going to process all of the out edges from vertex 2. Now, when we do that, we have, we have to also push vertex 2 onto the active stack. Okay, when we do that, we discover that we have this out edge from vertex 2 back to vertex 1. Now, in this case, discovered for vertex 1 is true. And the entry time for vertex 1 is less than the entry time for vertex 2. So when that happens, we have discovered an edge that leads from our vertex that we're exploring back to an ancestor of that particular vertex. We also know that this is an ancestor because we have not yet finished processing number 1. We'll talk about that in more detail later, but if we discover an edge to a vertex that has already been discovered and not yet processed, then we have discovered a back edge. And when we have a back edge, suddenly the lowest vertex that we can reach from this vertex that we were exploring may now become lower, right? In particular, the entry time of vertex number 1, which is 1, is less than the current low for vertex number 2 here, because the low for vertex number 2 is, well, vertex 2, and that has an entry time of 2. So we can get to an earlier vertex than vertex number 2. That is, we can get to vertex number 1. So we mark the low 1. And then, because this vertex had already been discovered, we don't need to conduct a search of it, which means we are done processing this edge, and we return to processing any other edges of vertex 2. There aren't any other edges out of vertex 2, so that means that we have to exit vertex 2, which means we're going to process it late. So in processing vertex 2 late, we are going to first check to see whether low is equal to the value of 2 itself, which it's not actually, and that's interesting. So that means from vertex 2, we can get to a vertex earlier than vertex 2. That also tells us that from the parent of vertex 2, we could get to that same vertex, right? That is, from the parent of vertex 2, we can get to vertex 2. And from vertex 2, we can get to some earlier vertex. That means if the low of vertex 2 is lower than is an earlier vertex than its parent's low, then we can now assign the parent's low to be vertex 2's low, because we can get to that low from the parent. Now, of course, we don't have to do that in this case, because the low of the parent of vertex 2 is not any earlier of a vertex than the low of 2. As a matter of fact, it's the same vertex, it's vertex 1. So we don't have to do any reassignment here. That's all we have to check as we leave vertex 2 here. We now mark vertex 2 as processed, but notice that we do not pop it off the active stack at this point. We have not yet found the strongly connected component completely, of which vertex 2 is a member, unlike in our previous example, where as we left vertex 2, we knew the strongly connected component consisted just of vertex 2. So here, we have an edge that goes back to some earlier vertex. That means there's going to be a cycle from some earlier vertex up to vertex 2, which means vertex 2 is going to be part of some strongly connected component that includes some of its own ancestors, right? And in this case, it's just going to be its only ancestor, vertex 1. But how does the algorithm tell us that? Well, the algorithm goes back and sees that vertex 1, well, first of all, we've now processed all edges from vertex 1, so we don't need to continue processing the edges from vertex 1, which means we're about to leave vertex 1 and return to its parent, if it had one, which means we process it late, which means we compare its low value to itself, and we say, is this low value equal to 1? And it is. And what that means is, always, we've found a strongly connected component. So we increment the components found by 1. And now we are going to pop components off the active stack. So we are going to pop vertices off this active stack, and all of the vertices on the active stack down to the current vertex should be part of the same strongly connected component. That is our big trick. And how do we know that's going to be the case? Well, we know that the low of vertex 1 is itself, which means that you can't get back to any earlier ancestor of vertex 1. But we know that all of the vertices past vertex 1, from those vertices, you can always get back to vertex 1 from those vertices in some way. And again, we'll deal with more complicated examples in just a moment, but for now it should be clear that we can get back to vertex 1 from vertex 2 because we discovered this back edge. So it's appropriate for vertex 2 to be in the same strongly connected component as vertex 1. And we pop vertex 2 off of the active stack and set its strongly connected component equal to 1, meaning the first strongly connected component we have found for this graph. And then we also pop 1 off the active stack and set its strongly connected component to be 1. Okay, and then we can finish exiting vertex 1, processed equals true, and we have now completed our algorithm for this graph. Okay. So then we move on to a more complicated example. Oh, before we do, just commenting, both of these now say SCC equals 1, which means that the strongly connected component that they are both a part of is strongly connected component number 1. There is only one strongly connected component for the graph, which is why components found equals 1. Next example. Okay, so in this case we have, again, just a single line of descent from our starting node, or our starting vertex, in our depth first search. But we are going to have one back edge, and then we're going to have one vertex that's past that back edge. So we sort of expect, just on visual inspection, to get one strongly connected component for these two up here, and then a strongly connected component for this solo vertex down at the bottom. So let's talk about how that happens. Again, running the algorithm quickly from the beginning, we have time gets incremented to 1, the entry time is equal to 1, and discovered is set equal to true. We push vertex number 1 onto the active stack, and we continue to we proceed to process the edges out of vertex 1. So we process this edge here, and we discover that it's to an undiscovered vertex, vertex 2. So we are going to increment our time marker by 1, and entry time of vertex 2 is 2, and discovered for vertex 2 is true. And we push vertex 2 onto the active stack. We check all the vertices out of vertex 2. We have this all the edges out of vertex 2. We have this back edge, which points back to vertex 1, which has already been discovered. We do the same thing for this back edge that we did back in example 2, our second example, which is to mark the low of vertex 2 as vertex 1, because now it's possible to get back to vertex 1 via an edge directly from vertex 2. Okay, so we've processed that edge, and now we don't have to do any further processing because vertex 1 had already been discovered, so we don't have to do a search there. We continue back to vertex 2, and we look for other edges coming out of vertex 2, and we have this edge coming out from vertex 2 to vertex 3. Vertex 3 is undiscovered, so we are going to increment our time marker and set the entry time equal to 3, and say that vertex 3 has been discovered. Discovered equals true. And we push vertex 3 onto the active stack. We check to see whether there are any out edges from vertex 3. There are not any out edges, which means we proceed to process vertex 3 late before we exit from vertex 3. In processing it late, we check to see whether the low of vertex 3 is equal to 3 itself, which it is, which means we found a strongly connected component. We increment the components found by 1, and we mark the strongly connected component for vertex 3 to be 1. We also pop vertex 3 off the active stack. Okay, we finished processing vertex 3 late. We mark it processed. We return to vertex 2 and process any other edges out from vertex 2. There are none, which means we are done with vertex 2, but before we can depart from vertex 2, we must process it late. And in order to do so, we check to see whether the low of vertex 2, which is vertex 1, is equal to vertex 2 itself, which it's not, which means that vertex 2 is part of some strongly connected component that includes ancestors of vertex 2, which means that its parent vertex could also get to those ancestors. So the low of vertex 1, if it happens to be have a greater entry time, that is, if the low of vertex 1 happens to be a later vertex in the search than the low of vertex 2, we could replace vertex 1's low, but we don't have to because they are the same in this case. So now we are done processing vertex 2 late. We mark it as processed. However, we don't need to pop it off the active stack because we haven't found the complete strongly connected component of which vertex 2 is a member. So we return to processing vertex 1. We were in the middle of doing all of the out edges from vertex 1. We just did this edge, and there are no other out edges from vertex 1, so we're done with the edges out of vertex 1, which means we're about to leave vertex 1, so we need to process it late. And to process it late, we first consider whether the low is equal to the value itself, and the low of vertex 1 is equal to vertex 1, which means we have found a strongly connected component. We increment the number of strongly connected components by 1, and now we begin popping values off the active stack. We pop vertex 2 off the active stack. That's going to be in strongly connected component number 2, along with the next item down on the active stack, which is vertex number 1. And we set the strongly connected component for vertex number 1 to be 2. And then we have finished. All that remains is to mark processed as true for vertex 1. And we finished the algorithm. Now again, we ended up with 2 strongly connected components, exactly as we expected. Vertex number 3 is in the first strongly connected component that we verified, and vertices 2 and 1 are in the second strongly connected component that we verified. Okay, next example. We're going to work through essentially the same situation, but where the strongly connected component comes between vertices 2 and 3, and vertex 1 is all by itself in a strongly connected component, which we can see visually, and then we execute the algorithm to demonstrate it. So we have time equals 1, entry time equals 1, and vertex 1 has been discovered. That's true. Push vertex 1 onto the active stack and then explore its edges. We have this edge which we explore, discover an undiscovered vertex, mark it as discovered, increment the time marker by 1, and put in the entry time as 2. Push it onto the active stack, because again we have not yet found the strongly connected component in which it resides. We begin exploring the out edges from vertex 2. There's only this one. That takes us to vertex 3, which we mark as discovered. And we increment the time marker, and the entry time for vertex 3 is 3. And then we push vertex 3 into the active stack, and we start exploring the edges out of vertex 3. There is only one edge out of vertex 3, which points back to vertex 2. And vertex 2 has already been discovered, but it has not yet been processed, which means we're talking about a back edge from vertex 3 to vertex 2. So we check to see whether the current low of vertex 3, that is the earliest vertex that can be reached directly from one out edge from vertex 3, is earlier than this guy or not. This guy has an entry time of 3. The low of 3 is currently 3, which has the entry time for vertex 2 is 2. Entry time for vertex 3 is 3. So this one is lower than this one, which means we now set the lowest or earliest vertex that we can reach directly from vertex 3 to be vertex 2. That makes sense. And then we continue exploring the edges out of vertex 3, and there are no more edges, so we are ready to leave vertex 3, process it late, which means we are going to check to see whether its low is equal to its actual vertex value, and it is not. So then we allow its parent to have the same low value as vertex 3, because if we can get from vertex 3 to vertex 2, then we can get from whatever its parent is to vertex 2. And of course, we don't need to update this because the low of vertex 2 is already 2. Okay, so we have now finished processing vertex 3. We mark it as processed. And we don't push vertex 3 off the active stack yet because we still haven't found the strongly connected component in which vertex 3 resides. We return to vertex 2, we were processing its edges, we finished processing all of its edges now because there was only one. Then we're going to process vertex 2 late. We check to see whether low of vertex 2 is equal to 2 itself, and it is, and whenever that happens, it means we have found a strongly connected component. And again, the reason for that, which is evident with these two vertices, is that we can't get back to any earlier vertex in the tree from vertex 2, and we know that we are not going to be able to get back to any other earlier vertex in the tree by going forward to like vertex 3 and then going back somehow, because otherwise at some point along the line we would have reset 2's low to be some number less than 2, right? or to point to some earlier vertex in the graph besides 2. So because that never happened to us, we know that it's not possible to go forward from vertex 2 and then manage to get back to some earlier vertex, which means no ancestors of 2 are included in its strongly connected component, which means that 2 and 3 are our strongly connected component here. So now that we've found one strongly connected component, we start popping vertices off the stack and marking those with their strongly connected component. And we pop vertex 2 here off the stack and mark that with its strongly connected component number 1. And at that point we stop because it was vertex 2 that we discovered would be the early vertex in this strongly connected component. And we are now finished processing vertex 2 late. And we mark it as processed equals true. And we return to processing vertex 1. We were processing the edges out of vertex 1. There was only this one edge, so we're done processing the edges of vertex 1, which means now we can process vertex 1 late because we're about to exit it. We check to see whether low of 1 equals 1 itself, which it does, which means we have found another strongly connected component. And we pop vertex 1 off the stack and set its strongly connected component to be 2. It is part of the second strongly connected component that we have found in this graph. All right, then we finish processing vertex 1, so we mark it as processed, and we are done with our algorithm. Okay, notice that we ended up with 2 strongly connected components. Vertices 2 and 3 are in strongly connected component number 1, and vertex number 1 is in strongly connected component number 2. Next example. In this case, the entire graph is one big cycle, right? That is, we can start at vertex 1, go to vertex 2, go to vertex 3, and then go back to vertex 1. So we expect all 3 of these vertices to be in the same strongly connected component. Let's verify that that happens with our algorithm. So we set our time marker equal to 1. Entry time for vertex 1 is 1. Discovered equals true for vertex 1. And we push vertex 1 onto the active stack. We explore its edges, starting with this one. It's only out edge, which takes us to undiscovered vertex 2. We are going to increment our time marker by 1. Entry time for vertex 2 is 2. Discovered for vertex 2 is true. We have now seen this vertex. And we push vertex 2 onto the active stack. Then we explore the edges out of 2, and our edge takes us to vertex 3, which is undiscovered. So we increment our time marker by 1, and our entry time for vertex 3 is 3. We set discovered equal true for vertex 3. And then we process the out edges from vertex 3. We have this one out edge, which is a back edge to vertex 1. And therefore we say, well, we can get back to vertex 1 from vertex 3. And it is lower than 3's current low. Now you might ask, well, why do we always have to check whether it's lower than 3's current low? Doesn't it always end up being less than 3's current low? And the answer is it might not be if this weren't the first edge that we were processing out of 3, and there were another edge that went, say, from 3 back to some earlier vertex in the graph. And of course there are no earlier vertices in the graph, but if we had processed some other edge out of vertex 3 first, this low might have been set to some earlier vertex in the graph. And if that's the case, then we don't want to overwrite this low with this slightly later vertex in the graph, vertex 1, when we encounter this back edge. If there were an edge to an earlier vertex in the graph, then we would want this low to point to that earlier vertex. But of course there isn't. So we do actually set the low of vertex 3 to be vertex 1. And then we don't have to process vertex 1. We are now done processing the edges out of vertex 3, which means we are going to process it late. And we check to see whether low of vertex 3 equals 3, which it does not. So then we go up to its parent, and for the first time, now our parent gets the benefit of the lowest vertex that can be reached directly from vertex 3 via an edge. That is, because we know we can get from vertex 3 to vertex 1, we can definitely get from vertex 2 to vertex 1. And the low of vertex 2 is now set to vertex 1. Okay. We were still processing vertex 3 late, but now we have finished. And so we mark vertex 3 is processed. Oops, a long time ago I forgot to put vertex 3 on our active stack. It should have been on our active stack when we entered it. It was sitting there from a long time ago. I apologize for that. But it is still there is the important thing. We don't pop vertex 3 off the active stack because we have not yet found the earliest vertex in the strongly connected component of which vertex 3 is a member. So we now return to processing vertex 2. We were looking at the edges of vertex 2. We have now done all the edges, which means we're about to leave vertex 2. We process it late. We consider whether low of vertex 2 is equal to 2 itself, which it is not. So then we give its parent the benefit of that low vertex, that early vertex. But of course, the two lows are equal, so we don't need to reset the parent here. And we are done processing vertex 2. We exit from vertex 2 and return to vertex 1. We have now processed all the edges from vertex 1, so we process vertex 1 late, which means we need to check to see whether its low is equal to itself, which it is, which always means we have found a strongly connected component. Increment the components found by 1, and then slowly, one by one, go through the members of the active stack all the way down until 1, which is where we found that low equals the vertex itself. And for each of these that we pop off the active stack, we set its strongly connected component to be the current component, which is number 1. Pop off the 2, set that to be 1. Pop off the 1, and set that to be 1. Then we are done with vertex 1, mark it as processed, and we are done with the algorithm for the whole graph. Notice that we found one strongly connected component and every vertex in the graph is a member of that. Great. So our next example is a little bit, just the slightest little bit trickier. Here, we don't have one cycle for the whole graph, but let's see here. Would it be possible to get from any one of these vertices to any of the other vertices? Well, yeah, at the end of the day, we could get from vertex 1 to vertex 2 or vertex 3. That's clear. We could certainly get from vertex 1 to any of the others. From vertex 2, we could get back to vertex 1. From vertex 3, we could get back to vertex 2. But there is no direct edge from vertex 3 back to vertex 1. But that's okay, because of course we could take a trip from vertex 3 to vertex 2, and then from vertex 2 back to vertex 1. So we can get around anywhere we need to go in this graph, which means that it should all be one giant strongly connected component. Let's execute the algorithm and see what happens. Time equals 1, the entry time is 1, the first vertex is discovered, and we process it, we push it onto the active stack, we process its edges, starting with this one, we discover vertex 2, increment the time marker by 1, push vertex 2 onto the stack, and begin exploring its edges, including this one. We discover vertex 3, increment the time marker, mark the entry time, and mark vertex 3 as discovered, then push vertex 3 onto the active stack, and begin processing its edges, including this edge here, which we discover is a back edge, and it's pointing to a vertex that has an earlier entry time than vertex 3's current low's entry time. So we replace the current low with this vertex, and we have finished processing this edge, and all edges of vertex 3, we process it late. We ask whether 2 is equal to 3, that is the current low of vertex 3 is equal to 3 itself, which it is not, so we give its parent the benefit of pointing to whatever the earliest vertex we can reach from here is, and we don't have to change anything because its parent is already vertex 2. So we are done processing vertex 3. We return to vertex 2, we're done with its edges, so we process it late, and we check to see whether the low of 2 is equal to 2. Actually, we weren't finished processing the edges of vertex 2. I lied about that, sorry. We still had this edge to process that I should probably process in numerical order, but that's okay. We still have this edge to process from vertex 2. And this edge is a back edge to vertex 1. And vertex 1 is an earlier vertex than vertex 2 is, so we can replace vertex 2's low with vertex 1. And now we have explored all of the edges out of vertex 2. So then we ask ourselves, is vertex 1 equal to vertex 2? No, it's not, which means we leave vertex 2 on the active stack. We don't find a component, but we do give its parent, if necessary, the benefit of this low vertex that can be reached from vertex 2. And of course they are equal, so we don't need to update anything, which means we return to vertex 1 and mark vertex 2 as processed. And then from vertex 1, we have actually processed all of the edges from vertex 1, which means we can now exit from vertex 1, and we need to process it late. We ask, is 1 equal to 1, which it is. So we have found a strongly connected component. That is, we have found the earliest vertex in the strongly connected component consisting of 1 together with all of the items that are above it on the current active stack. Now, how did we know, and this is interesting, how do we know that we can get from any of these vertices after vertex 1 back to any other vertex? Well, we know for sure that we can get from 1 to any vertex in this list. So, if from any vertex in this list we can get back to vertex 1, then we know that we can get from any vertex to any vertex, right? So clearly we can see that there are paths, right? But how does the algorithm know that there are paths back to vertex 1 from vertices 2 and 3? Vertex 2, clearly there's a path back to vertex 1. If there had not been a path back to vertex 1, then the earliest vertex that we could have reached from vertex 2 would have been itself, which would have meant that 3 would have been cut off from 1. And that's the only way, really, that 3 could be cut off from 1, because we know that from 3 you can get to 2, right? So the only way that 3 could have been cut off from 1 is the case where you can't get from 2 back to 1, right? Now, if you hadn't been able to get from 2 back to 1, then the earliest reachable vertex from 2, or the low of 2, would have been 2 itself. And in that case, we would have stopped right here as we were leaving vertex 2 if low had been equal to 2, made a strongly connected component out of 2 and 3, and popped them off the stack, leaving only 1, as we did back in example 4. So we can be confident then that from all of these descendant vertices of vertex 1, we can get back to vertex 1, and we can get to all the descendants of vertex 1 from vertex 1, obviously. So then 1, together with all of its descendants on the active stack, are in a strongly connected component. So we pop all of the descendants, all of the items on the active stack off, and set their strongly connected component to be 1. Okay, great. So now we should talk briefly about forward edges. So it's possible that instead of having a back edge connecting two vertices that exist in the same sort of line of descent from our root vertex. We might have what we call a forward edge. Now notice that instead of pointing back from a descendant to its ancestor, this is pointing from some ancestor in the search tree to its descendant, and that's what we call a forward edge. We'll be able to recognize forward edges via some properties of discovery and processedness. Namely, we're going to discover vertex 3 first, and then we're going to process it. So both of these will be true by the time we get back to processing this particular edge right here. Running through the algorithm real quick goes like this: time equals 1, 1, we set this to be discovered, we push it onto the active stack, we process its first edge, which takes us here, we mark this as time equals 2, of course, because we increment the time. We mark this vertex as discovered. And we push it onto the active stack. And we process its edges. We discover vertex 3. We increment the time. We set the entry time. We mark it as discovered. We push it onto the active stack. We look at all of its out edges. There aren't any. We process it late. If this low is earlier than this low, then we give this one the benefit of this lower accessible vertex, but of course this one is not lower than its parent. As a matter of fact, I shouldn't have even done that. We compared this one to this. The low of this vertex is the vertex itself, which means we have found a strongly connected component. And we mark this as strongly connected component 1, and we pop vertex 3 off the active stack. We are now done with vertex 3. We mark it as processed and return to vertex 2. We've done all the edges from vertex 2. We process it late, and low of 2 is 2 itself, which means we have found a strongly connected component. We increment the strongly connected component count by 1. We pop 2 off the stack and mark this as strongly connected component number 2. We return to vertex 1, and at this point, we have only processed one of its edges. We now see this edge over here, which points forward, and we know it points forward because it is pointing to an edge that has already been discovered and that has already been processed and that has a later entry time than our current vertex number 1 that we are processing. So because the entry time is later than vertex number 1, we know that this has to be some kind of descendant of vertex 1, and this descendant has already been discovered, and so therefore this is a forward edge from vertex number 1. Okay, with forward edges, we do absolutely nothing. Convenient. So we have now processed all of the edges coming out of vertex 1, which means we process vertex 1 late. We ask, is low of 1 equal to 1? And yes, it is. So we increment the strongly connected components counter. We pop vertex 1 off the active stack, set this equal to 1 for a strongly connected component, and finish the algorithm by marking it as processed. We had 3 different strongly connected components in this case. All vertices 1, 2, and 3 were their own separate strongly connected components. Okay, so that covers all the cases where we have a single line of descent from our starting vertex in the depth first search. Most of the basic cases of interest. Now, the branching situations where we have multiple lines of descent from a vertex somewhere along the way all consist basically of those same essential problems of single lines of descent, but kind of happening multiple times. The tricky situation occurs when we happen to have a cross edge. So here in this first example, we don't have any cross edges. We'll execute our algorithm very quickly here. We set our time equal to 1. Entry time is 1. We discover our first vertex. We push it onto the active stack. And we process its edges, starting with this edge, takes us to an undiscovered vertex, which we now discover. We increment the time, and note the entry time, and process any edges out from vertex 2. There are no edges out from vertex 2, so we process it late and discover that its low is equal to itself, which means we found a strongly connected component. And so, oops, I forgot to push 2 onto the active stack when we entered it, but now I have remembered, and we are now going to pop 2 off the active stack because we found a strongly connected component, and we set its strongly connected component equal to 1. Okay, we return to processing the edges. Oops, we mark vertex 2 as processed, and we return to processing the edges of vertex 1. We find this edge to vertex 3, which is undiscovered. We increment the time marker by 1. We mark vertex 3 as discovered. We also push it onto the active stack, not forgetting this time. And then we look for edges out from vertex 3. There are none, so we process it late, discover that low of 3 equals 3, increment the components found, pop vertex 3 off of the active stack, and increment the strongly connected components, or rather, mark strongly connected component number 2 for vertex 3. It is its own strongly connected component. We return to vertex 1, continue processing the edges. There are none left to process, which means we process vertex number 1 late. And to do that, we check to see whether its low is equal to 1, which it is, so that means we found another strongly connected component. There are now 3. We pop vertex 1 off the active stack, and we set its strongly connected component to be 3. Finally, we mark it as processed, and we have finished our algorithm. We found 3 strongly connected components. Each vertex is its own strongly connected component because it's not possible to get from vertex 2 back to vertex 1 or from vertex 3 back to vertex 1 or anywhere else. So then they all have to be separate. Okay, the case of interest comes up next. Now, what I've done in the following cases in order to skip over a bunch of the grunt work to start with is to run the algorithm up to the point where we encounter a new kind of edge, specifically this cross edge right here between vertex 2 and vertex 3. So I've already pre-run the algorithm here to take us through vertex 1 and vertex 2. Vertex 2 is now marked processed. I haven't finished processing vertex 1 yet because I was working on this edge over to vertex 3 when I discovered this cross edge. What do I do with a cross edge, and how do I know it's a cross edge, first of all? So I see that this is a cross edge because it points to a vertex that has already been discovered and that has already been processed. So the entry time is less than the entry time for the vertex that I'm coming from, which means I must have hit it at some point earlier in the search. But it's been processed, which means it cannot be an ancestor of the vertex that I am currently searching from. If it had been an ancestor of the vertex that I'm currently searching from, it would not yet have been fully processed because I only mark a vertex processed when I'm kind of backing out of the search tree from that vertex. So I know that this vertex, because it has been processed, cannot be an ancestor, and yet it has an earlier entry time. If it has an earlier entry time and it's not an ancestor, then it means it has to have some kind of brother-sister kind of relationship, or maybe some kind of cousin or second cousin relationship, not a direct ancestor or a direct descendant. Hence we call it a cross edge. Okay, so then at this point, vertex 2 has already been marked within its own strongly connected component. We found that from vertex 2 you couldn't get to any other vertices, so when we were doing vertex 2 earlier, we marked vertex 2 as being in its own strongly connected component. And as a matter of fact, for visual clarity, I'm going to mark it in red to indicate that from this vertex you can only get to other red vertices and you can get nowhere else. So then my question is it possible that by using this edge from vertex 3 to vertex 2, that is by passing through vertex 2, you could somehow get from vertex 3 to one of its ancestors, one of the ancestors of vertex 3? Because if that were possible, then we would hold on to hope that maybe vertex 3 could be part of a strongly connected component with one of its ancestors via this path, right? That is via vertex 2. But we know that vertex 2 doesn't go back to any of the ancestors of vertex 3 because it is its own strongly connected component. And you might say, well, how do we know that it's not in a strongly connected component with any of the ancestors, right? Like, how do we know that just because we've marked this as having a strongly connected component, how do we know that, like, for instance, vertex number 1 isn't in that strongly connected component, and therefore I could get from 3 over to 2 and back to vertex 1 and then make a strongly connected component out of the whole graph, right? And the answer to that question is that vertex 1 has not yet been processed, has not yet been fully processed. So that means there's no way we could possibly know for sure the complete extent of the strongly connected component in which vertex 1 lies, which means it can't be in this strongly connected component with vertex 2. So any ancestor of vertex 3, that is, cannot be in any strongly connected component whose full extent has been explored just yet, because we're still exploring vertex 3, right? So then we know finally, after all that thinking, that we are not going to get anywhere with vertex 2 in terms of getting back to an ancestor of vertex 3. So this edge does not help us, which means that we don't mark our low as any lower than it already is for vertex 3. And we are now done processing the edge, and we continue to process any remaining edges from vertex 3. There are no remaining edges from vertex 3, so we process vertex 3 late, discover that low of vertex 3 is 3 itself, which means we have found another strongly connected component, and we increment our components found to 2, pop vertex 3 off of the active stack, and mark it with 2 for its strongly connected component. All right, now we have finished vertex 3, mark it as processed, return to vertex 1. Vertex 1 now has a low that is equal to itself, and we increment the components found to the 3, pop 1 off the active stack, mark its strongly connected component as 3, and mark it as processed. Our algorithm is complete. We have 3 separate strongly connected components in this situation. In our next situation, we have essentially the same 3 vertices, but now we add a back edge from vertex 2 back to vertex 1. So notice I've marked these 2 in green. Again, I'm imagining that I have run the algorithm on vertex 1, I've found vertex 2, I found this back edge, I've marked these guys, and then I've marked over to here, or I've explored over to vertex 3, and now I am at the point where I am looking at this cross edge. And this cross edge takes me back over to vertex 2, just like before. But now vertex 2 has not yet been marked as being in its own strongly connected component. It's not been marked as being in any strongly connected component. And that means that the lowest vertex that we can reach from 2 must have been less than 2 itself, which means we can get back to an ancestor of 2 from 2. Now, that's interesting. That's useful information to us because that leaves open the possibility then that from vertex 3 we could get back to an ancestor of vertex 3 by going over to vertex 2 first. And as a matter of fact, we can get back to vertex number 1. Now, how do we know that we can get back to do we know that we can get back to an ancestor of vertex 3 from vertex 2? We know we can get back to one of vertex 2's ancestors, but we're not sure that we can get back to one of vertex 3's ancestors. Well, we don't know, but what we do know is that whatever the low of this thing is, number 2, we can get there from vertex 3. And it's lower than the current low of vertex 3, so I'm going to replace the low of vertex 3 with vertex 1, because I know I can get back to vertex 1 because I can get to vertex 2. Okay, so then I don't have to conduct a search of vertex 2 because I've already done it, so I'm done with this edge, and I'm done with all the edges from vertex 3. I ask myself, is the low of vertex 3 equal to vertex 3? And it is not. It's less than vertex 3, which means vertex 3 is in some strongly connected component with one of its ancestors. I give its parent the benefit of being able to get to whatever this low value is here, and I don't need to update it because it's already 1. So I'm now done processing vertex 3. I mark it as processed, and I return to vertex 1. I have now processed all of the out edges from vertex 1, namely this one and this one, which means I process vertex 1 late. Its low value is equal to itself, which means I found a strongly connected component, and all of the items on the stack, all the vertices on the active stack, all the way down to vertex 1 are in that same strongly connected component. I pop them off one at a time and mark each of them with strongly connected component 1. And now I'm done with the algorithm. Mark this one processed just for fun. Okay. And we're done with the algorithm. We found that all of these vertices are in fact in the same strongly connected component. There is only one of them. I had marked these guys with green, by the way, to indicate that they were connected to each other, and therefore, but we hadn't yet finished finding the strongly connected component that involved these guys necessarily, for sure, in the same way that we had over here. In this example, we had already finished finding the strongly connected component that vertex 2 was a part of. We know it didn't contain any other vertices. Alright, so we go to our next example now, which is basically like the example we just did, except instead of vertices 2 and 3, which again have this cross edge, that's going to be consistent, by the way. Our cross edge is going to be between vertices 2 and 3. Instead of vertices 2 and 3 being brothers, shall we say, vertices 2 and 3 are now some kind of cousins. I don't know enough about genealogy to tell you for sure which kind of cousins. Maybe it's like second cousins or cousins once removed or something like that. In any case, vertex 2 and vertex 3 are some kind of cousins. Vertex 3's grandparent is vertex 2's parent in our search tree. Okay, and the question is, well, does this make a difference in how things work out? And intuitively it should be no, because we have a cycle in this graph, right? We could go from 1 to 4 to 3 to 2 back to 1. And so it shouldn't make a difference. So I've executed our algorithm all the way up to the point where we are processing this cross edge. And again, we know it's a cross edge because the entry time for vertex 2 is less than the entry time for vertex 3. And the discovered vertex 2 has already been discovered, and it has already been fully processed, right? But it hasn't been assigned to a strongly connected component, which means that you can get from vertex 2 back to one of vertex 2's ancestors. And furthermore, that ancestor from that ancestor, you might be able to get to, say, vertex 3, which would make a cycle. So we set vertex 3's low to be 1, just as we did before, because we know we can get from vertex 3 to vertex 2, and we can get from vertex 2 to whatever low of vertex 2 is. And we have finished processing all the edges out of vertex 3. We mark, or we check to see whether low of 3 is equal to 3, which it is not. So we haven't found a strongly connected component yet. We now give 3's parent the benefit of the lowest vertex that can be reached by using a back edge from 3. And that is now vertex 1. So if we can get from vertex 3 to vertex 1, then we know we can get from vertex 4 to vertex 3, so we can certainly get from vertex 4 all the way back to vertex 1. And vertex 1 is the lowest vertex we can get, earliest vertex we can get to from vertex 4. Okay, so we have now finished processing vertex 3. We mark it as processed. We return to vertex 4 and process it late. 1 is not equal to 4, which means we give the parent the ability to access vertex 1. And of course, 1 can already access vertex 1. We don't need to update it. We are now done with this vertex. We mark it processed and return to vertex 1. We had already processed this edge, and now we've processed this edge. Therefore, all the edges of vertex 1 are done, and we process it late. And we check to see whether 1 equals 1, and in fact it does, which means we found a strongly connected component. And all of the current items on the active stack are going to get popped off, and we're going to write strongly 1 into each of these strongly connected components. I'm not going to bother to do that right now for time purposes, but that's exactly what we would do, and we would have one nice strongly connected component consisting of all of the vertices of the graph. Next, in this situation, instead of having an extra family member in between our root vertex and vertex 3, we have an extra family member in between our root vertex and vertex 2. And again, I have executed the algorithm all the way up to the point where we are processing this cross edge between vertex 3 and vertex 2. And again, it's in this interesting situation where we have a back edge from vertex 2 back to vertex 1. So at this point, I know that all of these vertices marked in green here are going to be part of some strongly connected component. I just don't know the full extent of that strongly connected component yet. I don't know whether it's going to include any vertices that are over here as like another child of number 1, right? It's part of another child of part of a different line of inheritance from vertex number 1. So when I discover this cross edge, I say to myself, okay, well, is there a strongly connected component assigned to vertex 2 already? No, which means that I should check to see what the lowest vertex that is that I can get to from vertex number 2, at least relatively directly, and that lowest vertex is vertex number 1. So if I can get from vertex 2 to vertex 1, and I can get from vertex 3 to vertex 2, then I can certainly get from vertex 3 to vertex 1. So its lowest is now 1, the lowest we've seen so far. Finish processing the edges here, we process it late. 1 is not equal to 3, which means that I give its parent, which is 1, the benefit of being able to get to this particular vertex. But of course, I don't need to update, so then I'm done processing vertex 3. Mark it as processed, return to vertex 1. I have now processed all out edges from vertex 1. I process vertex 1 late, which means that I check to see whether low of 1 equals 1. It does. I increment the components found, and then I pop all of these vertices off the stack and and mark each of their strongly connected components as 1. Again, I am going to skip that step for time purposes. Okay, then we have this situation where vertex 2 points to some ancestor of the most recent common ancestor of vertex 2 and vertex 3. Notice that in examples, these examples, the two preceding examples, from vertex 2 you were able to get back to exactly the most recent common ancestor of vertex 2 and vertex 3. That was true also over here. From vertex 2 you're able to get back to the most recent common ancestor of vertex 2 and 3. Here, we're not able to get back to the most recent common ancestor. We're actually able to get back to an earlier common ancestor than that. But in this case, it's going to end up working out the same. We're still going to have a single strongly connected component for the entire graph. Okay. Now, I'm not going to bother to finish working this out here, but I will give a very quick summary, which is that since this strongly connected component is not set, this guy can get to 0, which means its parent can get to 0, but we already knew that, so we don't have to bother to reset it. And then, since you can get to 0 from everybody, you can get to the entire graph, and it is one strongly connected component. Okay. Now this is the interesting situation. These three situations were all pretty much the same. In each one of these situations, you were able to get from this target of the cross edge back to some ancestor of the source of the cross edge. That is the vertex from which the cross edge was drawn, right? So whenever that happens, you're going to have a cycle that's formed by the cross edge, and you're going to have a strongly connected component, right? Cycle that goes all the way from 1 to 2 to 3 and back to 1, etc. And a cycle that goes from 0 to 1 to 3 to 2 to 0, right? But in this case, the target of the cross edge is not in a strongly connected component with any ancestor of the source of the cross edge over here. And notice that when this happens, it happens to be the case that the strongly connected component has already been assigned for vertex 2. Why is that the strongly connected component has already been assigned? Well, suppose that in this graph it were possible to get from vertex 2 back to some earlier ancestor than vertex 5, like for instance vertex 1, right? That is, suppose it were possible to get all the way back from vertex 2 to some common ancestor with vertex 3. If that were the case, then we would not yet have marked vertex 2 with a strongly connected component. Because if it were possible to get from vertex 2 back to vertex 1, then we would not yet have, because we have not yet finished processing all of vertex 1's edges, we wouldn't have known the full extent of the strongly connected component contained in that contains vertex 2 and vertex 1. So we would not have yet marked it as being part of some fixed strongly connected component. So therefore, it's not possible for any ancestor of vertex 3 to be reachable from vertex 2, because we know the extent of the strongly connected component that vertex 2 has. And of course, from any ancestor of vertex 3, by the way, from any ancestor of vertex 3 at 1 or earlier, we could get to vertex 2, so that would be part of the strongly connected component. So it's not possible to get from vertex 2 back to any ancestor of vertex 3, which means we don't need to worry about this cross edge. It's not going to complete any cycles for us. It's not going to contribute to any strong connectedness of the graph. Therefore, when we see this cross edge that points to a vertex that has already been assigned a strongly connected component, we simply ignore this cross edge. We return to vertex 3 and we ask ourselves, well, are there any other edges out from it? No. So is low of 3 equal to 3? Yes, it is. Now components found equals 2, and oops, vertex 3 should have been on the active stack here. Should have been right there. I forgot to push that on earlier. Now it's gone in any case, and I mark its strongly connected component as component number 2. Then I return to its parent, and I discover that this parent vertex has no more edges, and therefore I check to see whether 1 is 1. It is. Increment the components found to 3, pop 1 off the active stack, and mark its strongly connected component as 3. Therefore, there are 3 strongly connected components in this graph, the first of which consists of these 2 red vertices, the second of which consists of the sole vertex 3, and the third of which consists of the sole vertex 1. And that is all.